So for this is your third calculus-based physics thing. This is on page 122 in your book. So we're just going to talk about this problem. It's already in your book, but we're just going to go through it. So this is it's where the force on an object is dependent upon the velocity. And one of the cases is the friction due to air friction on a body. If you have two solids like this, a block, and it moves along this surface parallel, so the two flat surfaces are parallel to each other, the force is not dependent upon the velocity, or we assume it's not dependent enough that we worry about it, so we assume the force is constant and the friction force is equal to the coefficient of friction, which in this case would be kinetic because it's moving, times the normal force, which is usually the weight unless somebody's pushing down on it. Now if something's going in the air, falling in the air, there is a friction force, and it's not constant. It increases with velocity. Sometimes it may actually be more related to velocity squared, but that's a problem that's hard to solve. So Newton's second law says that the sum of the forces is equal to the mass times the acceleration. But the acceleration is just dv dt, the derivative of the velocity vector with respect to time. So that's acceleration, and that's equal to forces. So if you have a body that's falling, you're going to have the weight, which is constant, pushing down, and you're going to have this friction force pushing up. So that friction force. And what we're going to do is assume that it's proportional to the there's some proportionality constant. And interestingly enough, they also say that, no, well, what are they doing here? Oh, okay. I was wondering where the heck did they get that from. But, so the weight is equal to the mass times acceleration due to gravity, and the friction force pushing up is going to be proportional to, it's going to be some proportionality constant. In the book, they use B times the velocity. So if we substitute those in, and let's define y positive going up. They actually define y positive going down. So y positive is going down. So what we get is the weight's going down, so it's positive. So you get m times g, and then you have the force, friction force, which is going the opposite direction. You get b times v. And if you divide both sides by n, you get, and this is all one-dimensional, so we can get rid of the vector thing. So dv dt is equal to g minus b over m times the velocity. So this is acceleration due to gravity, which is 9.8 meters per second squared. And this is this constant relating the friction force to the velocity, and m is the mass because we divided everything by mass. So what this is a first-order linear differential equation, and let's rewrite v dv dt as v prime. Let's move the velocity term to the left-hand side of the equation and leave the g over there. So first-order linear differential equation is in standard form. Remember p, we always say p of x, but in this case it's a function of t. V is a function of t, so p of t is b over m. So our integrating factor, we're going to use integrating factor here, is that the integrating factor is the integral e to the integral of p of t dt. So we get e to the integral of b over m, which is a constant, times dt. So you take the constants outside, and then you have the integral of dt, which is just t. So our integrating factor is b over n times t. And the next step in an integrating factor problem is we multiply everything by the integrating factor. So here it is. Here's the original differential equation. And what happens is you can, this times that plus this times that, you can collapse into the integrating factor b e to the b over m t times just the variable by itself, and then you put the prime out front. And over here we have g e to the b over m times t. So the whole purpose of the integrating factor is to allow you to take these two terms, one that involves derivative, one involves just a function, and collapse them together. So when you integrate this, when you integrate both sides like that, the left-hand side just becomes e to the b over m times t times v. So the integral of something primed is just that something. On the right-hand side, we get the constant g is brought out. When you integrate this, you divide by this coefficient. So I'm just going to multiply by the reciprocal instead. So instead of dividing by b over m, I'm going to multiply by m over b. And then you get the same argument, same thing, e to the b over mt, and you get an arbitrary constant. And so you're going to have some initial velocity, which if we assume that the initial velocity is equal to 0, so v of 0 equals 0, velocity at t equals 0 equals 0. But before we do that, let's multiply by everything here by the term, but we're going to change the exponents to negative like that. So as a result, this times that, you get negative 1, you get 0, because you add this to that, you get 0. So you get e to the 0, so you solve for v of t, and the same thing happens here, so you get m times g over b. So this times that is also e to the 0, which is 1. And we get plus c, and multiply by e to the minus b over m times t. So now we apply the initial condition, b of t equals 0 equals 0. So this goes to 0, and you get m times g over b plus c e to the 0 power, because I have t equals 0, so the whole thing here is 0. E to the 0 is 1. And if I solve for c, it's negative mg over b. So when I plug that back into my, this is called the general solution. What we're getting now is the particular solution. So we get mg over b, which is this term right there, minus mg over b times e to the minus b over mt. And we factor out the mg over b times 1 minus e to the b over mt, close the parentheses. So you can see at t equals 0, I get this e to the 0, and it's e to the 0 is 1, so you get 1 minus 1 is 0, so you get, this works out correctly. V of 0 equals 0, which is what we wanted to happen relative to the initial conditions. As you let t go to infinity, this term goes to 0, and so v at t equals infinity, which I guess is really not entirely kosher, is equal to mg over b. And if you wanted to look at the acceleration, and the acceleration is dv dt. So I take the derivative of this with respect to time. This first term goes to 0. So what I'll end up with is mg over b, which is the constant, and I'll have a negative. And the derivative of this is just the coefficient, d over m, e to the b over m t. There's a minus sign there, forgot that. So the acceleration is a function of time. The b's cancel out, the m's cancel out. I get negative g e to the minus b over mt. So at t equals 0, a is equal to negative g e to the 0, because this whole thing becomes 0, the exponent becomes 0, which is e to the 0 is 1, so you get at t equals 0, the acceleration is negative g, and at t equals infinity, I get a e to the g, e to the negative infinity, and that is 0. So at the terminal speed, when it stops, the acceleration is its maximum. I mean, the velocity is at the maximum, the acceleration goes to 0. So there you go. That's an example of where you have the force is not a constant, but is a function of the velocity.